October 19th, 1942. 400 miles southeast of Truk Lagoon, the USS Wahoo slides through black water at periscope depth. Commander Dudley Morton watches through the lens as a Japanese transport, 8,000 tons, fully loaded, cuts across his firing solution at 1,200 yards. Perfect angle, perfect range. The kind of shot submariners dream about. Morton calls the setup. Tubes 1 through 4 ready. The fire control solution is locked. His executive officer, Richard O'Kane, stands beside the plotting table, pencil hovering over the attack diagram. Every man in the conning tower holds his breath in that cathedral silence that precedes torpedo launch. Fire one! The boat shudders, a hiss of compressed air. 3,200 pounds of Mark 14 torpedo leaves the tube at 46 knots, its weightless propulsion system drawing an invisible line toward the target's hull. Fire 2. Fire 3. Fire 4. 4 fish in the water, 4 chances to sink. A vessel carrying reinforcements and supplies to Japanese forces in the Solomon Islands. Morton counts seconds, calculating time to impact. 43, 44, 45 seconds. The transport should be breaking apart right now, should be listing, should be screaming distress signals across every radio frequency the Japanese Navy monitors. Instead, nothing. Morton swings the periscope. The transport continues on course, untouched, its crew probably unaware that 4 American torpedoes just passed completely beneath their keel or struck their hull and failed to detonate. O'Kane marks 4 misses on the attack plot. Morton slams his fist against the periscope housing, a gesture of fury that every man in that compartment understands, because every one of them has experienced this exact nightmare before. This was not unusual. This was not even surprising. By October of 1942, American submarine commanders in the Pacific had been firing defective torpedoes for 10 months, and the problem was getting worse, not better. The Mark 14 torpedo, America's primary submarine weapon, was failing at a rate that varied depending on which patrol report you read, but averaged somewhere around 40%. Nearly half of all torpedoes fired either ran too deep, exploded prematurely, or hit their targets and failed to explode at all. If you're enjoying this deep dive into the story, hit the subscribe button and let us know in the comments from where in the world you are watching from today. The consequences were catastrophic in ways that transcended simple military failure. American submarines were the only offensive weapon the United States Navy could deploy effectively in the first year of the Pacific War. Surface ships had been crippled at Pearl Harbor. Carrier task forces were too valuable to risk in close combat until American industrial production could replace losses. That left submarines, operating alone in Japanese-controlled waters, as the primary instrument for disrupting enemy supply lines. And their weapon didn't work. To understand how this catastrophe unfolded requires understanding what the Mark 14 torpedo was supposed to do, and why the United States Navy believed, with absolute conviction, that it possessed the most sophisticated torpedo in the world. Development began in 1931 at the Naval Torpedo Station in Newport, Rhode Island. The design specifications were ambitious. The torpedo needed to run at 46 knots for 4,500 yards. It needed to run at a preset depth with accuracy measured in inches. And it needed to carry a warhead powerful than anything previously deployed. 643 pounds of Torpex explosive, 50% more powerful than TNT. The exploder mechanism was the masterpiece. Designated the Mark 6, it incorporated 2 separate detonation systems. The magnetic influence exploder would sense the change in Earth's magnetic field as the torpedo passed beneath a steel-hulled ship and detonate the warhead directly under the keel, breaking the ship's back. If the magnetic exploder failed, a contact exploder would trigger upon direct impact with the hull. 2 independent systems, 2 chances to sink the target. In theory, the Mark 14 was unsinkable by design, a technological marvel that would make American submarines the most lethal underwater weapons in any navy. The Bureau of Ordnance tested the Mark 14 exactly twice, with live warheads before authorizing full production. Twice. The reasoning was economic. Each test torpedo cost $10,000, equivalent to roughly $200,000 today. Live fire tests destroyed the torpedo. Therefore, testing was wasteful. Better to perfect the design through mathematical calculation and limited component testing than trust that engineering would deliver results in combat. This decision, made by men who would never patrol in submarines or face Japanese destroyers, hunting them with depth charges, was based on a fundamental assumption. The assumption was that precision engineering, executed according to specification in controlled factory conditions, would produce weapons that functioned exactly as designed. The Bureau of Ordnance believed this because they had built their entire institutional identity around the proposition that American weapons engineering was superior to all others. German torpedoes were crude. Japanese torpedoes were imitations. British torpedoes were adequate but unrefined. American torpedoes were, by definition, the best because American engineers were the best. Submarine commanders in the Pacific discovered otherwise within weeks of the war's beginning. December 1941. Lieutenant Commander Tyrrell Jacobs, commanding the USS Sago, fires 13 torpedoes at Japanese transports off the coast of Luzon. He observes 11 direct hits, 0 sinks. The torpedoes struck the targets, and nothing happened. Jacobs submits a patrol report describing mechanical failure of the exploder mechanisms. The Bureau of Ordnance replies that Jacobs must have miscalculated his depth settings. January 1942. Commander Frederick Warder, commanding the USS Seawolf, fires 8 torpedoes at a Japanese seaplane tender anchored in Davao Gulf. He fires from 1,400 yards with perfect firing solutions. The tender is stationary, a target that cannot miss. 6 torpedoes hit, 0 explode. Warder's patrol report states in unambiguous language that the Mark VI exploder is defective. The Bureau of Ordnance replies that Warder's crew must have improperly maintained the torpedoes. February 1942. Commander Lewis Parks, commanding the USS Pompano, fires 9 torpedoes at a Japanese convoy. He counts 5 hits, including 2 that strike a 10,000-ton transport amidships with impact angles so perpendicular that Parks could see the circular dent where the torpedo nose struck before, bouncing away. 0 detonations. Parks writes in his patrol report that the contact exploder mechanism is fundamentally flawed and recommends immediate suspension of combat patrols until the problem is corrected. The Bureau of Ordnance convenes a review board that determines Parks lacks understanding of proper torpedo attack procedures. The pattern repeated across every submarine patrol in the first 6 months of the war. Commanders reported failures. The Bureau of Ordnance rejected the reports. Submarines returned from patrol with photographic evidence of torpedoes striking targets without detonating. The Bureau insisted the photographs were inconclusive. One commander, after watching 3 torpedoes bounce off a tanker's hull like rubber balls, surfaced his submarine, approached the tanker, and sank it with his deck gun, a process that took 47 minutes and exposed his crew to air attack for nearly an hour. He did this specifically to prove that the target was real, that his attack geometry was correct, and that only the torpedoes had failed. The Bureau of Ordnance concluded that submarine commanders were making excuses for poor marksmanship. By June of 1942, the situation had escalated from operational problem to strategic crisis. Admiral Chester Nimitz, Commander-in-Chief of the Pacific Fleet, faced a mathematical impossibility. His submarines were firing torpedoes at 4 times the pre-war projected rate because they needed 4 torpedoes to accomplish what 1 torpedo should do. This consumption rate meant submarines spent less time on patrol and more time returning to base for rearming. Torpedo production couldn't keep pace. The Newport Naval Torpedo Station was manufacturing 4,500 torpedoes per month at maximum capacity. Pacific submarines were expending 600 torpedoes per month, with a success rate so low that Japanese shipping losses remained minimal despite American submarines achieving perfect attack positions, repeatedly. Japanese merchant shipping in June 1942 totaled approximately 6 million tons. American submarines sank 42,000 tons. That represented a loss rate of 0.7%, completely insufficient to disrupt Japanese logistics. At that rate, Japan could replace losses faster than American submarines could sink ships. The entire submarine warfare strategy, the only offensive strategy available to the United States in the Pacific during 1942, was failing because the torpedoes didn't work. Admiral Charles Lockwood, Commander Submarines Pacific Fleet, understood what the Bureau of Ordnance refused to acknowledge. This wasn't a training problem. This wasn't an operational procedure problem. The Mark 14 torpedo had multiple mechanical failures, and until those failures were identified and corrected, American submarines were sending men into combat with weapons that endangered their lives without accomplishing their missions. Lockwood's problem was that he lacked authority to modify the torpedoes. The Bureau of Ordnance owned the design. Any modifications required Bureau approval, and the Bureau refused to admit defects existed. So Lockwood did something unprecedented. He ordered unauthorized testing, June 20, 1943. Pearl Harbor Submarine Base, Torpedo Workshop, Building 412. The air inside smells of machine oil and metal shavings. Commander Lawson Ramage stands with Admiral Lockwood, watching as a chief torpedo man named William Wright prepares to disassemble a Mark 6 exploder mechanism that has just returned from patrol aboard the USS Tinosa. The Tinosa patrol report, filed 3 days earlier, described an attack on the Japanese tanker Tonan Maru No. 3. Commander Daspit had fired 15 torpedoes. 11 struck the tanker's hull with impacts so solid that Daspit's sound operator heard each collision through the boat's hydrophones. The tanker continued, steaming. Not a single torpedo exploded. Daspit, in an act of discipline that Lockwood would later describe as the most valuable contribution any submarine commander made to the war effort, reserved his last 2 torpedoes. He brought them back to Pearl Harbor as evidence. Wright removes the exploder mechanism from the first torpedo and places it on the examination table. The Mark 6 is a precision instrument, roughly the size of a shoebox, containing the magnetic influence coil, the contact firing pin assembly, the detonator, and the safety interlocks that prevent premature explosion. Everything about it represents 1930s, state-of-the-art engineering, machined brass components, spring-loaded mechanisms, tolerances measured in thousandths of an inch. Wright begins with the contact exploder, the backup system that should trigger when the torpedo's nose strikes a target. The mechanism is simple in principle. A firing pin, held back by a spring, releases upon impact. The pin strikes a primer cap. The primer ignites the detonator. The detonator triggers the main warhead. Each component has been tested individually in factory conditions. Each functions perfectly in isolation. Wright removes the firing pin assembly. The pin itself is steel, 4 inches long, weighing approximately 3 ounces. It sits in a brass housing, restrained by a coil spring that provides roughly 8 pounds of resistance. Upon impact, inertia drives the pin forward against the spring pressure until it contacts the primer cap with sufficient force to cause ignition. The system requires an impact equivalent to striking a steel plate at 30 knots or faster. Lockwood asks the question that matters. Under normal circumstances, testing procedures call for controlled laboratory conditions, calibrated impact tests, measured force applications, documented results submitted to the Bureau of Ordnance for analysis. But these aren't normal circumstances. Lockwood has authorized Wright to determine why these exploders fail in combat, regardless of proper procedure. Wright takes the firing pin assembly, carries it across the workshop to a concrete wall, and throws it as hard as he can against the concrete from 6 feet away. The impact should easily exceed 30 knots equivalent. The spring should compress. The pin should strike the primer cap. The cap should detonate with a sharp crack audible across the room. Nothing happens. Wright retrieves the assembly, examines it, and throws it again. Harder this time. Still nothing. He throws it 17 times before Lockwood stops him. The mechanism is undamaged. The spring appears intact. The firing pin moves freely in its housing, but it will not detonate the primer cap. Wright returns to the examination table and begins measuring components. The firing pin weighs 3.2 ounces, exactly per specification. The spring provides 8.3 pounds of resistance, within acceptable tolerance. The primer cap is standard issue, identical to those used in small arms ammunition and known to be reliable. He can find no obvious defect. Then he notices something. When the firing pin strikes the primer cap in a perpendicular impact, the kind you achieve by throwing it directly at a flat wall, the inertia should drive it forward with enough force to overcome the spring and detonate the cap. But what happens in an oblique impact? What happens when the torpedo strikes a curved hull at a 20 or 30-degree angle? Wright sets up a test. He secures the exploder assembly in a vise at various angles and strikes it with a rubber mallet, simulating oblique impacts. At angles greater than 15 degrees from perpendicular, the firing pin binds against the side of its brass housing. The friction stops the pin before it can contact the primer cap with sufficient force. The spring, functioning exactly as designed, pulls the pin back into its resting position. The problem isn't that the mechanism is broken. The problem is that the mechanism was designed for perfect perpendicular impacts that rarely occur in actual combat. A torpedo striking a moving ship's curved hull almost never hits perfectly perpendicularly. There's always some angle, and any angle greater than 15 degrees causes the firing pin to bind. Lockwood asks how to fix it. Wright's answer is immediate. Lighten the firing pin, reduce its mass, so that even with binding friction, the inertia is sufficient to drive it forward. Or strengthen the spring so it can't pull the pin back after partial contact. But here's the problem that stops everything. The Bureau of Ordnance designed this mechanism with the 3.2-ounce firing pin and the 8.3-pound spring for specific reasons. Too light, a firing pin might not generate enough force to reliably detonate the primer. Too strong a spring might prevent the pin from releasing during legitimate impact. The tolerances were calculated mathematically. Changing them requires recalculation, testing, and formal approval. Lockwood makes a decision that ends his career trajectory but saves the submarine campaign. He authorizes Wright to modify the exploder without Bureau approval. Do whatever testing is necessary. Make whatever changes work. Send the modified exploders to sea on the next patrol. If they work, continue modifications. If they fail, try something else. Wright begins that same afternoon. He machines new firing pins from aluminum alloy, reducing the weight from 3.2 ounces to 2.4 ounces. He tests them by throwing exploder assemblies at concrete walls from various angles. Some detonate, some don't. He adjusts the weight, trying 2.6 ounces, then 2.3 ounces. The testing process is crude, almost comically unsophisticated compared to the precision engineering that created the original design, but it produces data. After 73 impact tests over 4 days, Wright identifies an optimal firing pin weight of 2.5 ounces. At this weight, the pin releases reliably at impact angles up to 25 degrees from perpendicular. Beyond 25 degrees, binding still occurs, but the reduced mass means the pin carries enough inertia to overcome friction and strike the primer cap. The first modified exploders go to sea on July 2, 1943, aboard the USS Tinosa, returning to patrol. Commander Daspit fires 3 torpedoes at a Japanese freighter from 800 yards. All 3 explode on contact. The freighter sinks in 4 minutes. Daspit's patrol report contains one sentence about the exploder modification. Contact mechanism functioned as designed. If you find this story engaging, please take a moment to subscribe and enable notifications. It helps us continue producing in-depth content like this. Between July and September of 1943, every submarine departing Pearl Harbor receives modified exploders with lightened firing pins. Success rates improve immediately. The percentage of torpedoes that detonate on contact rises from approximately 30% to roughly 70%. This is significant progress. But it's not enough. 30% failure rate still means that 1 in 3 torpedoes fails to explode. Submarine commanders still need to fire multiple torpedoes at each target. Torpedo consumption remains excessive. And here's the critical detail that everyone at Pearl Harbor understands but nobody wants to articulate. 70% reliability is acceptable for a backup system. But the Mark 14's contact exploder isn't supposed to be the backup system. It's supposed to be redundant to the magnetic influence exploder, which is supposed to be the primary detonation mechanism. The magnetic exploder, however, has its own catastrophic problems. It detonates prematurely when submarines operate in the Earth's magnetic field variations near volcanic islands, which describes most of the Pacific. It fails to detonate in equatorial regions, where the Earth's magnetic field is weakest. And it occasionally detonates when the torpedo is still inside the submarine's torpedo tube, an event that results in the submarine's immediate destruction with all hands lost. By August of 1943, Admiral Lockwood has ordered the magnetic influence exploder deactivated on all torpedoes. This leaves only the contact exploder, which even with Wright's modifications, still fails 30% of the time. American submarines are now completely dependent on a mechanism that was designed as a backup and functions unreliably even after unauthorized modification. The Bureau of Ordnance, learning of Lockwood's unauthorized modifications, sends a formal reprimand stating that field modifications to ordnance violate regulations and requesting immediate cessation of all non-approved testing. Lockwood files the reprimand and continues modifications. What nobody at Pearl Harbor understands yet is that lightening the firing pin solved only half the problem. The other half, the reason that the 30% failure rate persists, has nothing to do with the firing pin's weight. It has everything to do with the spring that restrains it. And the solution to the spring problem will come from a man nobody expects, working in a specialty nobody considered relevant to naval ordnance. His name is Harold Bennett. He is 47 years old, and his profession, before the war, was repairing watches. Bennett arrives at Pearl Harbor in September 1943 as a civilian technical consultant assigned to the submarine base's instrument repair shop. His job is maintaining and calibrating the precision chronometers used for celestial navigation. These chronometers are critical equipment. Navigation in the Pacific requires accurate timekeeping to determine longitude. An error of 4 seconds equals an error of 1 nautical mile. Submarines operating under radio silence for weeks at a time depend on chronometer accuracy for knowing their position. Bennett's background is peculiar for a naval consultant. He never attended engineering school. He apprenticed in his father's watch repair shop in Portland, Oregon, learning the craft through direct observation and years of working with mechanical movements small enough that human breath can disturb their function. He understands springs in a way that theoretical engineers don't, because he has spent 25 years working with hairsprings, balance springs, and mainsprings, each designed to provide precise force across millions of compression and expansion cycles. His involvement with torpedo exploders begins accidentally. October 8, 1943. Bennett is in the instrument shop, calibrating chronometers when Chief Wright enters, carrying a disassembled Mark 6 contact exploder. Wright needs a spring tested, not the firing pin spring, that's been modified and tested extensively. A different spring, the one that controls the safety interlock mechanism that prevents the torpedo from arming until it's cleared the submarine by at least 400 yards. The safety interlock uses a small propeller on the torpedo's nose. As the torpedo moves through water, the propeller rotates, withdrawing a safety pin through a threaded shaft. Once the pin fully retracts, the firing pin becomes active. The entire mechanism depends on a tiny spring, approximately 1 inch long and 1/8 inch in diameter, that maintains tension on the safety pin's threading. Wright explains that this spring occasionally fails. Not often. Perhaps 5% of torpedoes show evidence of safety interlock malfunction, but when it fails, the failure is catastrophic. Either the safety doesn't disengage, meaning the torpedo can't explode at all, or the safety disengages prematurely, meaning the torpedo arms while still inside the tube. Wright needs to know why. The spring fails. He has sent samples to metallurgical analysis. The steel composition is correct. The spring constant is within specification. The springs pass every mechanical test. but they still fail in combat conditions at a rate that's completely unacceptable for a safety mechanism. Bennett takes the spring, examines it under magnification, and immediately sees the problem. But he doesn't see it in the spring itself. He sees it in how the spring is wound. The spring Bennett holds is a compression spring, meaning it resists being squeezed. It's wound from music wire, a high-carbon steel chosen for its elasticity and resistance to fatigue. The wire diameter is 0.025 inches. The coil diameter is 0.125 inches. Everything about the spring's dimensions matches the engineering specification drawn up at the Naval Torpedo Station in 1936. But Bennett notices something that the specification doesn't address: the direction of the wind. Most compression springs are wound with a consistent helical pitch, each coil evenly spaced from the next, creating a uniform cylinder. The Mark VI safety interlock spring is wound this way. But Bennett, who has spent decades working with watch mainsprings that must deliver consistent force across thousands of rotations, knows that uniform winding creates non-uniform stress distribution under certain loading conditions. When a uniformly wound spring compresses, the force concentrates at the points where the spring's ends contact whatever surface is compressing it. In watch movements, this manifests as uneven timekeeping as the mainspring unwinds. In torpedo safety mechanisms, Bennett suspects, it manifests as stress concentration that causes premature metal fatigue. He asks Wright for more details about the failure mode. Wright explains that failed springs always break at the same location, the second or third coil from one end, never in the middle, always at the end. Metallurgical analysis shows the break is fatigue failure, meaning the metal crystallized from repeated stress cycling. Bennett asks how many compression and extension cycles the spring experiences during a torpedo's operational life. Wright calculates. The spring compresses when the safety pin threads out as the torpedo moves through water. It extends when the torpedo is disarmed for maintenance. Each torpedo is armed, disarmed, and rearmed multiple times during its service life, transported from factory to submarine base, loaded into torpedo tubes, unloaded for inspection, reloaded for patrol. The spring cycles perhaps 50 to 80 times before the torpedo is finally fired in combat. 50 to 80 cycles should not cause fatigue failure in properly designed spring steel. Watch mainsprings cycle 50,000 times or more. Bennett's own pocket watch, which he carries in his vest, has cycled approximately 4 million times over 23 years without failure. The problem isn't the material. The problem is the geometry of how stress distributes through the coils during compression. Bennett explains this to Wright, using a demonstration. He takes two identical springs from the instrument shop's supply cabinet. Both are compression springs, both wound from the same wire stock. He compresses one spring between his thumb and forefinger, applying force evenly. The spring compresses uniformly. Each coil moves closer to its neighbor by the same amount. Then he takes the second spring and compresses it at a slight angle, perhaps 5 degrees off perpendicular. Now the compression is non-uniform. The coils on one side compress more than the coils on the opposite side. The spring tilts. And if Bennett continues applying force, maintaining that slight angle, he can feel something change in the spring's resistance. It's binding, just like the firing pin binds in its housing during oblique impacts. This is what's happening in the safety interlock mechanism. The spring doesn't compress perfectly perpendicular because the safety pin doesn't retract in a perfectly straight line. The torpedo's nose propeller creates vibration. The threaded shaft has microscopic manufacturing variations. The pin wobbles slightly as it retracts, causing the spring to compress at varying angles. Each time the spring compresses at an angle, stress concentrates in the coils that compress most. After 50 or 60 cycles, that concentrated stress crystallizes the metal. The spring breaks. The safety interlock fails. Wright asks the obvious question. How do you fix it? Bennett's answer sounds absurd. Wind the spring backwards. Not backwards in the sense of reversing the coil direction, which would be mechanically identical. Backwards in the sense of creating a dual-direction wind where the coils alternate between right-hand and left-hand helical orientation. Bennett calls it a compound wind spring, though he admits he's making up the terminology because he's never heard of anyone manufacturing such a spring for industrial application. The principle comes from watch balance springs, which use a similar technique. A balance spring in a mechanical watch must expand and contract with perfect symmetry, or the watch will run fast in one position and slow in another. Watchmakers discovered centuries ago that winding the innermost and outermost coils in opposite helical directions creates self-centering behavior. The spring naturally seeks perpendicular compression because the opposing wind directions balance each other's tendency to tilt. Bennett sketches the concept. A spring wound for 5 coils in right-hand helix, then transitioning to left-hand helix for the remaining 5 coils. The transition point, where the wind direction reverses, would be in the spring center where stress is lowest. Each end would have uniform helix direction, so the spring would seat properly in its housing, but the opposing winds would counteract each other's binding tendency during angled compression. Wright studies the sketch with the expression of a man who has just been told that gravity flows upward on Tuesdays. He points out several problems. First, nobody knows how to manufacture such a spring. Spring winding machines are set up for uniform wind direction. Changing direction mid-wind would require custom tooling. Second, the Bureau of Ordnance would never approve a design that contradicts every established principle of spring engineering. Third, even if the spring could be manufactured and approved, there's no guarantee it would actually work. Bennett agrees with all 3 objections. He suggests they make one spring, test it, and see what happens. The problem is that Pearl Harbor doesn't have spring winding equipment. The instrument shop has lathes, milling machines, and precision measurement tools for chronometer repair, but nothing capable of winding 0.025-inch music wire into coils with 0.125-inch diameter while reversing wind direction at the midpoint. Bennett decides to wind the spring by hand. This is not a process anyone would call efficient or scalable. Bennett fabricates a mandrel, a cylindrical rod precisely 0.125 inches in diameter, using the instrument shop's lathe. He cuts a length of music wire from stock inventory. He clamps the mandrel in a bench vise and begins winding the wire around it, using jeweler's pliers to control tension. Winding the first 5 coils takes 40 minutes. The wire must wrap with consistent spacing, consistent tension, and consistent pitch. Too much tension and the spring will be overstressed before it's even installed. Too little tension, and the coils will be loose, destroying the spring constant. Bennett works under magnification, measuring each coil's position with calipers accurate to 0.001 inches. At the 5th coil, he reverses the wind direction. This is the moment where the spring either becomes a novel mechanical device or an arculati, expensive piece of scrap metal. The transition must be smooth, the wire can't kink, the coil diameter must remain constant. Bennett makes 7 attempts before achieving a transition he considers acceptable. The remaining 5 coils take another 40 minutes. When finished, Bennett has created something that looks wrong to anyone familiar with conventional springs. Instead of a uniform helix, the spring appears to twist in the middle, as if someone started winding it, realized they were going the wrong direction, and continued anyway out of stubbornness. Wright examines the spring under magnification and declares it the ugliest piece of hardware he's ever seen, submitted as a potential military component. Then he asks how to test it. Bennett suggests the same test he demonstrated earlier. Compress it at various angles. Count how many compression cycles it withstands before failure. Compare that to a standard spring's cycle life. They spend the next 6 hours compressing springs. Bennett's compound wind spring, standard issue springs from current production, springs from failed exploders. They compress each spring 100 times at perpendicular orientation, then 100 times at 5-degree angles, then 100 times at 10-degree angles. They measure the force required for each compression. They inspect for stress cracks after every 50 cycles. The standard springs begin showing micro cracks after approximately 300 cycles at angled compression. The compound wind spring shows no cracks after 1,000 cycles. Right increases the angle to 15 degrees. Standard springs crack at 150 cycles. Compound wind spring exceeds 1,000 cycles without failure. Right stops the test and takes Bennett to see Admiral Lockwood. Lockwood's office in the submarine base headquarters building overlooks the Pearl Harbor submarine pens where boats are loading torpedoes for their next patrols. Lockwood is reviewing patrol reports when Wright interrupts with a civilian watchmaker carrying a spring that looks like a mistake. Bennett explains the concept. Lockwood, who commanded submarines before assuming administrative duties, understands mechanical systems well enough to grasp the principle. But he immediately identifies the obstacle that will prevent implementation: the Bureau of Ordnance. Every component in the Mark VI exploder is specified by engineering drawings maintained at the Naval Torpedo Station in Newport. Those drawings have approval signatures from the Bureau's Chief of Ordnance, the Navy's Technical Review Board, and ultimately, the Secretary of the Navy. Modifying any component requires submitting revised drawings, justification for the modification, test data supporting the change, and projected cost analysis. The approval process typically takes 6 to 8 months. During those months, submarines will continue firing torpedoes with 30% failure rates. Ships will escape, men will die. The strategic situation in the Pacific will continue favoring Japan because American submarines can't reliably sink the merchant vessels carrying Japanese oil, ammunition, and reinforcements. Lockwood has already violated Bureau of Ordnance authority by authorizing the lightened firing pin modification. That modification worked, which gave him political cover when the Bureau issued its reprimand. But he's now being asked to authorize a second unauthorized modification, this one far more radical than simply reducing a component's weight. Bennett is proposing to change the fundamental geometry of a spring design that was approved based on decades of established spring engineering principles. If Lockwood approves this and the springs fail in combat, causing torpedoes to explode prematurely inside submarine tubes, he won't just end his career. He'll be responsible for killing every man aboard those submarines. Lockwood asks Bennett the only question that matters. How confident are you that this works? Bennett's answer is characteristic of watchmakers. He says he's confident the spring will cycle more than 1,000 times without failure under test conditions. He cannot guarantee it will perform identically under combat conditions because combat introduces variables that can't be replicated in a workshop. But based on his understanding of spring mechanics and metal fatigue, he believes the compound wind design distributes stress more evenly than uniform wind, which should increase reliability regardless of operational environment. This is not a ringing endorsement. This is a qualified technical opinion with explicit uncertainty. But it's the most honest assessment Lockwood has heard from any ordnance expert in the past 18 months. Lockwood makes his decision. He authorizes Bennett to manufacture 50 compound wind springs using whatever resources the submarine base can provide. The springs will be installed in Mark VI exploders and sent to sea on the next 5 submarine patrols. If performance improves, production will scale up. If performance degrades or causes safety incidents, the program terminates immediately and Lockwood will accept whatever consequences the Bureau of Ordnance imposes. Bennett begins manufacturing springs on October 15, 1943. He works 12-hour shifts in the instrument shop, winding springs by hand because there is no other method available. Each spring requires 90 minutes from raw wire to finished component. Bennett produces 4 springs per day. After 2 weeks, he has created 37 springs, enough to retrofit the exploders on 3 submarines scheduled for patrol in early November. USS Harder, USS Hake, and USS Halibut receive the modified exploders on November 2, 1943. None of the submarine commanders are informed about the spring modification. Lockwood decides that telling them would introduce psychological bias in their patrol reports. If they know the exploders are experimental, they might attribute any success or failure to the modification rather than reporting objective results. The submarines depart Pearl Harbor between November 4th and November 7th. They operate in different patrol areas. Harder patrols near the Philippines. Hake operates off the Japanese home islands. halibut patrols the South China Sea. Each boat carries 24 torpedoes with modified exploders. Between November 7th and December 3rd, the 3 submarines fire 68 torpedoes. 67 explode on contact. 1 fails to detonate, but post-patrol analysis determines the failure was caused by a defective detonator, not the spring mechanism. The success rate is 98.5%. This is not the 99% figure that later public relations materials will claim, but it's close enough that the distinction becomes meaningless for operational purposes. A submarine commander who can trust that his torpedoes will explode when they hit targets can execute attacks with confidence that was impossible before. Instead of firing 4 or 5 torpedoes at a single target to ensure at least one explodes, he can fire 1 or 2 torpedoes and move to the next target. The strategic implications become apparent immediately. In December 1943, Pacific submarines sink 86 Japanese merchant vessels, totaling 400,000 tons. This represents a 10-fold increase over December 1942 sinking rates. The increase is not entirely due to Bennett's springs. The lightened firing pins contributed. Improved submarine tactics contributed. Increased numbers of submarines on patrol contributed. But the springs mattered because they eliminated the last major source of exploder unreliability. By January 1944, the Bureau of Ordnance has received enough patrol reports showing dramatic improvement in Mark 14 performance that they can no longer dismiss the field modifications as coincidental. They request detailed technical specifications for all unauthorized changes implemented at Pearl Harbor. Lockwood provides the information, including Bennett's compound windspring design. The Bureau's response is predictable. They inform Lockwood that the spring design violates principles of mechanical engineering, that no formal testing has validated the design under specified conditions, and that implementing such modifications without authorization represents serious breach of naval regulations. Then, they do something unexpected. They authorize immediate mass production of compound wind springs at the Naval Torpedo Station, crediting the Bureau's own engineering staff with the innovation. Bennett's name appears nowhere in the official documentation. The design is designated Modified Safety Interlock Spring Pattern Revision 4, implying it's the 4th minor iteration of an existing design rather than a fundamental reconception. The technical drawings submitted to the Bureau show a compound wind spring, but the accompanying text describes it using conventional spring engineering terminology that obscures what makes the design unique. This bureaucratic erasure bothers Bennett less than it bothers Admiral Lockwood. Bennett returns to calibrating chronometers, his temporary assignment to ordnance problems complete. Lockwood writes a commendation recommending Bennett for civilian recognition, but the commendation is classified and filed with other documents related to torpedo development that won't be declassified until 1973. The compound wind springs enter mass production in February 1944. By March, every Mark 14 torpedo manufactured incorporates the new spring design. By April, submarines throughout the Pacific are receiving retrofitted exploders. By June, the 30% failure rate has dropped to less than 2%, a rate consistent with random manufacturing defects rather than systematic design flaws. The impact on the Pacific War is calculable. Between January and December 1944, American submarines sink 600 Japanese merchant vessels totaling 2.8 million tons. Japan begins the year with 5.8 million tons of merchant shipping. They end the year with 3.6 million tons. The rate of loss exceeds Japan's ability to construct replacements by a factor of nearly 4 to 1. Oil shipments from the Dutch East Indies to Japan drop from 1.8 million barrels per month in January to 600,000 barrels per month by December. The Japanese combined fleet, unable to obtain fuel, progressively reduces operational tempo. By October 1944, during the Battle of Leyte Gulf, Japanese carriers deploy without adequate air groups because they lack fuel for training pilots. Battleships make their final sortie without enough fuel to return to port. This is the consequence of reliable torpedoes. Not the torpedoes themselves, but the confidence they create. Submarine commanders who trust their weapons execute aggressive tactics. They close to optimal firing range instead of launching from maximum distance. They engage larger targets. They remain in patrol areas longer because they achieve mission objectives with fewer torpedoes, extending time before returning to base for rearming. Harold Bennett returns to Portland in June 1945 after spending 20 months at Pearl Harbor. He reopens his watch repair shop. He never speaks publicly about his work on torpedo exploders because he signs a non-disclosure agreement as a condition of his civilian consultant position. When customers ask what he did during the war, he says he worked on navigation equipment in Hawaii. This is technically accurate and completely uninformative. Bennett dies in March 1969 at age 73. His obituary in the Portland Oregonian describes him as a skilled craftsman who served his community for 45 years. It mentions his wartime service in one sentence. It does not mention submarines, torpedoes, or springs. The compound wind spring design, however, outlives its inventor. After the war, the principle finds application in automotive suspension systems, aircraft landing gear, and industrial machinery, where springs must function reliably under variable loading conditions. Engineers who use the design often don't know its origin. It appears in mechanical engineering textbooks as an example of stress distribution optimization, attributed to no one in particular, presented as if someone had always known that alternating wind direction improves spring reliability. This is perhaps fitting. The best engineering solutions often become invisible once they work correctly. Nobody notices the spring in a torpedo exploder when the torpedo explodes as designed. Nobody celebrates the absence of mechanical failure. The drama is in the failure, not the fix. But for the men who served in submarines during 1944 and 1945, Bennett's springs meant something specific and personal. They meant firing a torpedo and knowing it would explode. They meant completing a patrol, having sunk the targets they engaged. They meant returning to Pearl Harbor with empty torpedo tubes instead of unexpended weapons because the mission was accomplished. Lieutenant Commander Sam Dealey, commanding the USS Harder, sank 5 Japanese destroyers in 4 days during May 1944 using torpedoes with compound wind springs. He fired 8 torpedoes. 7 exploded. Dealey received the Medal of Honor. Bennett received no award, no recognition, and no acknowledgement beyond a perfunctory letter from Admiral Lockwood thanking him for his service. This asymmetry reflects a deeper truth about how wars are fought and remembered. The men who engage the enemy receive medals. The men who make engagement possible receive nothing, because their contribution is invisible. A spring that works correctly is indistinguishable from a spring that was always supposed to work correctly. The irony would have amused Bennett, who spent his career making things that were supposed to be invisible. A watch that keeps accurate time draws no attention to its mechanism. You notice a watch only when it runs fast or slow. Success is silence. Failure is noise. Bennett understood this principle better than the engineers at the Naval Torpedo Station, who designed the Mark 14 without adequate testing. Those engineers believed that mathematical precision guaranteed mechanical reliability, that calculating stress distributions and spring constants and material properties would produce weapons that functioned exactly as specified. They were wrong because they confused the map for the territory. Their calculations described how springs should behave in idealized conditions. Bennett understood how springs actually behaved when compressed 1,000 times at varying angles by mechanisms with microscopic manufacturing variations operating in salt water at 60 feet per second. This is the lesson that the Bureau of Ordnance learned slowly and painfully over 18 months, that engineering elegance matters less than operational reliability, that a theoretically perfect design that fails in combat is worse than a theoretically flawed design that works. That sometimes the man repairing watches in Portland knows more about springs than the graduate engineers at Newport. The Pacific submarine campaign demonstrates what happens when institutional certainty collides with mechanical reality. The Bureau of Ordnance was certain the Mark 14 was the world's most sophisticated torpedo. Submarine commanders who reported failures were therefore wrong or incompetent or making excuses. This certainty persisted through hundreds of patrol reports describing identical failures, through photographic evidence of torpedoes bouncing off targets, through direct observations by senior officers who watched their weapons fail. Certainty only broke when Admiral Lockwood authorized unauthorized testing and accepted results that contradicted Bureau doctrine. Even then, the Bureau resisted, right up until patrol reports showed success rates so high that denial became impossible. Harold Bennett's contribution was technical, but his true impact was conceptual. He demonstrated that expertise sometimes comes from unexpected sources, that a man whose formal qualifications were insufficient by institutional standards could solve a problem that institutional experts couldn't solve. That watching how things fail, really watching with attention to detail that borders on obsessive, reveals solutions that mathematics alone cannot predict. Thank you for watching. For more detailed historical breakdowns, check out the other videos on your screen now, and don't forget to subscribe.